Hola, buenos días. Uh, yo hago, yo hago dos ninja stars. ¿Ustedes quieren mis ninja stars? No quieren. Okay, I'm going to get started. Good morning, everyone. I hope you had a good weekend. Mr. P here. And let's go ahead and get started with the lesson. Should be a pretty straightforward lesson today. So, here we go. No one reacted to my ninja stars. Okay. So let's talk a little bit about last time. Last time we learned about what is called elastic potential energy, U sub E, which is 1/2 kx squared. And that's basically the energy stored in a compressed spring or a stretched rubber band or things of that nature. Okay? And then we learned about work, which is a transfer of energy from one system to another. And we learned basically how is the law of conservation of energy affected by work being done on a particular system. And basically it works just like accounting. Okay, we think about energy like money. If you have $10 in your bank account and then someone gives you $5, you now have $15 in your bank account. Okay, similarly, if you have an initial amount of energy E naught, someone does an amount of work W on you, you now have an amount of energy equal to E naught plus W. Okay? So it's just accounting. That's all it is. Even my brother, who's an accountant, could understand it. Okay? I just dissed my brother. I hope he's not watching. All right, so this time we're going to focus a lot more on work. So today's lesson is about how to calculate work. Okay? And so there are a number of different um, scenarios that I want you to know about where you're going to be calculating work. So I'm just going to go through 3 different scenarios where that I might present to you where you'll need to calculate work. Okay, so scenario 1 is a constant force that makes a certain angle with the displacement. So it's important to realize that you might apply a force in a certain direction. The object does not necessarily move in that direction. Okay? So for example, what if I have my calculator here, sitting on my desk? Okay? I'm applying a force that's angled downward, but the calculator moves side to side. Okay? So the force that I apply is in one direction, but the displacement is in a different direction. Okay? So yeah. The force and the displacement do not need to be in the same direction. So we might have a situation like this. So you have a force that's going in this direction, but the displacement is in another direction. Okay? And so there's going to be some angle theta between the force and the displacement. And so in this case, the formula for work is F parallel times the size of the displacement. Okay? F parallel times the size of the displacement. So what do I mean by F parallel? This is the component of the force parallel to delta x. Okay? So you would calculate that using trigonometry. So for example, F parallel, you would make a force triangle right here. This would be F perpendicular because this leg of the triangle is perpendicular to the displacement. This would be F parallel. So you use trigonometry to find that leg of the triangle and then multiply that by the displacement. Okay? So this would be an example of positive work being done because F parallel is positive and the displacement is positive. You could imagine a situation like this. What if we had a force like this and a displacement like that? Okay. Bug just farted. I don't know if you could hear that. In this case, we have F parallel is like this. So we can see that F parallel is actually in the negative direction and delta x is in the positive direction. So this would be a scenario where we have work less than 0, negative work being done. Okay, this would be at work greater than 0. We could have a situation like this where you have a displacement this way and you have a force this way. In this case, our F parallel is negative and our displacement is also negative. So we have a negative times a negative, which is a positive. So this would be positive work done. Okay. And lastly, we could have a situation where the displacement and the force are perpendicular to each other. So if you have a force that's perpendicular to the displacement, then there is no parallel component. So this is a work of 0. All right? So depending on sort of the angle between the force and the displacement, you can have either negative work done or positive work done, or in fact 0 work done. You have 0 work done when they're perpendicular to each other. Because if they're perpendicular, there is no parallel component. Okay, so let's do an example. Let's suppose we have a box that is on the surface. It doesn't matter what the mass of the box is. Okay, and someone is dragging the box with a force. Okay, the force is 120 newtons, and it makes an angle of 40 degrees with the horizontal. Okay, the box is dragged let's say maybe 5 meters to the right. Calculate the work. Okay, so in this case, what we would do is I'd make a little diagram. So here's 120 newtons. Here is 40 degrees. Okay, and the displacement is going this way. So 5 meters. So I have to find F parallel, which I can see is the leg of the triangle that is adjacent to the angle. So that means that my F parallel in this case is going to be 120 cosine of 40 degrees, which I would plug into the calculator. And I get about 92 newtons is F parallel. Okay, so now my work done is F parallel times the displacement, which is going to be 92 times delta x, which is 5. 90 times 5 is 450, and plus 10, 460 joules of work were done. Okay? So that's one way to calculate a work. You have a constant force that makes a certain angle with the displacement. Okay? The second way in which you might be asked to calculate work is like so. You have, so the second way is if you have a non-constant force acting parallel to the displacement. So if you have a non-constant force, then in order to describe that force, you need to have a force versus position graph. Okay, because that just, you need a graph to describe the way in which it's not constant. So maybe we have a force versus displacement graph that looks like this, or I don't know. In that case, the work is the area under the curve. And this would be F parallel. Okay, so this is the second way in which you might be asked to calculate work. Okay, so let's do an example. Okay, let's suppose that um, a 6 kilogram object initially at rest experiences the force time graph, or the force position, excuse me, shown below. Okay, so I'm going to draw the force position graph. So we have force versus position. So here's F parallel. Here's position. And it looks like this. And then it drops to 0. Okay, so this is 10 meters. This is 4 meters. And the maximum force is 100 newtons. Okay, so to calculate the work, I'm going to do triangle plus rectangle. Okay, so I calculate the work. This triangle, its base is 4, its height is 100. So 400 divided by 2, this is 200 joules of work for the triangle. And then I have a rectangle that is 6 by 100. Okay, so that's going to be 600 joules of work. So the total amount of work done is going to be 200 plus 600, 800 joules of work. Okay, now what we want to know is, what is the final velocity of the mass? Okay, so to do this, we're going to use the law of energy conservation in open systems. So if you have an open system, all right, the initial energy plus the work done is equal to the final energy. Okay, now because the 6 kilogram object is initially at rest, it starts out with no kinetic energy, so the initial energy is 0. The amount of work done is 800 joules. And that 800 joules becomes the kinetic energy of the object. So the way that it works is, the work that is done on an object becomes one of the forms of energy that we learned about. So the work that you do becomes kinetic energy, for example. The work that you do becomes gravitational potential energy. The work that you do becomes elastic potential energy. So that, the work that you do is you're giving energy to something, and then that energy has to manifest itself in some way. So it has to be one of the forms of energy that we know about. Okay? So in this case, the object is speeding up, so this is becoming kinetic energy. So it's 1/2 m, which is 6, times v squared. Okay, so I have 800 equals 3v squared. Divide both sides by 3, take the square root. And we get that the final velocity is going to be 16.3 meters per second. Okay, so that's the second way of calculating work, if you have a non-constant force acting parallel to the displacement. The third way, so the third and final way of calculating work, is okay, the third way is to deduce the amount of work based on the change in energy of the object. Okay, so for example, if you started out with 3 joules of energy, and then later on I see that you now have 10 joules of energy, I can deduce that something did 7 joules of work on you, because where else would that energy have come from? Okay, so it's based on the equation E initial plus the work done is E final. And so if I just subtract E initial over to the other side, I get that the work done is equal to the change in energy of the object. Okay? So let's see how that works. Let's say a 50 kilogram space probe its speed increases from 200 meters per second to 300 meters per second. How much work was done on the space probe? Okay, so this is happening in outer space, so we don't really have gravitational potential energy. We don't need to worry about that. So I'm going to use the work done is equal to the change in energy. So it starts out with kinetic energy. It ends up with even more kinetic energy. So the final energy is going to be 1/2 times 50 times 300 squared. That's the final energy because it ends up with a velocity of 300 meters per second. The initial energy was the kinetic energy of traveling at 200 meters per second, so 100 times 50 times 200 squared. And then I subtract those two. That's the change in energy, so that would be the amount of work done. Oops, I don't know why I put 500. That should be 50. And we get 1.25 times 10 to the 6th joules of work was done. Now you can have a very large amount of work done. I think one of the questions in the quiz today has like billions of joules of work done, so don't panic about that. It's just we have a lot of energy. It's okay. All right, so these are the 3 ways that you can calculate work. So let me review them. The first way is if you have a constant force that is making a certain angle with the displacement. In that case, it is F parallel times the displacement. All right. If you have a non-constant force that is acting parallel to the displacement, you would take the area under the force position graph. Okay? The third way, which always works no matter what, is you look at the change in energy of the object and you subtract the final energy from the initial energy, and that's the amount of work done. Okay? So there's one case that we didn't cover, which is what if you have a non-constant force that is not parallel to the displacement? So it's like a combination of number 2 and number 1. And in that case, you need calculus. And it's probably not something you would learn until you were in college. So I'm not going to worry about that situation. All right. This is going to be a two-pager today. So I did want to talk about just some other things. And I was reading a book. Ooh, let me grab it. So over the summer, I was reading this book. It's called Structures or Why Things Don't Fall Down. I would highly recommend it. It's an excellent book. Structures or Why Things Don't Fall Down. And it just talks about like a lot of really cool, like random mechanical engineering topics. And one of the topics that I thought was really interesting was it was talking about bow and arrows and ballistas and different like medieval weapons. And it said something in the book that I thought was really cool. So it asked the question, why is a bow and arrow or why is a bow, I guess, already taught before you use it? Before firing, I should say. Have you thought about, a bow? You have to take the bow and you have to flex it and attach the string to it. And so the bow begins in the already flexed state. Okay? So why is the bow already flexed when you're using a bow and arrow? Okay? And there's a reason for that, and it has to do with work. Okay? So if we think about it, let's suppose that the bowstring began flimsy. What would the force versus displacement graph look like? If the string begins flimsy, then it takes almost no effort to pull it back initially. Okay? So the force versus displacement kind of looks like this. Okay? So in this case, the bow is not taut at first. Okay? The bow is not taut at first. And we know it wasn't taut at first because the force starts at 0. And of course, displacement is position is how far back you pull the bowstring. Okay? So because it started out flimsy, it took no effort at first. Okay? But what if we start out with the bow already taut? Okay? In that case, the force required to make the bowstring come back is non-zero right at the beginning. So it starts at some non-zero value, and then it goes up from there. So this is what happens when the bow starts out taut. There's basically a y-intercept in this graph. Okay? Now, why is this better than this? Well, if we think about it, how much work is done on the bow in this case? In this case, the amount of work done is simply that amount right there. Okay? But if the bow starts out taut, then the amount of work done is actually all of this. So we can see that there's a huge difference in the amount of work done because we have all of this extra area up here. Okay? So what that translates to is that the bow has much more elastic potential energy stored in it, so that when you let go of the bowstring, that elastic potential energy becomes the kinetic energy of the arrow, and so basically the arrow is going to go a lot faster. Okay? So I had never heard it, or never read it, I should say, explained in that way before, and I just thought that made so much sense. You know, it's like you want the bow to be taut so that when you fire you can store more elastic potential energy. So anyways, maybe that doesn't make any sense, but I thought it was a cool thing. All right. So the last thing I wanted to talk about today is something called power. Okay. So power is denoted by P, and power is equal to the work that you do divided by the time it took. Okay, so power is work divided by time. All right, power is work divided by time. So what would be the units of power? The units of power, well, work is measured in joules and time is measured in seconds. Work divided by time, so it's joules per second. Okay, this has a special name. It is called the watt, W. So power is measured in watts. Okay, power is measured in watts. So there's a joke in physics, which is, what is the unit of power? That's a question. And then the response is, watt is the unit of power. Okay? So that's how you can remember it. Power is work divided by time. So let's do some examples, just a couple of examples with power. What is the average power output of a human? What is the average power output of a human? Okay, and I say average because the power output of a human can change depending on what the human is doing. If you're sleeping, you're not doing any work, so you have no power output. But if you're sprinting, you know, you're lifting things, then you have a much larger power output. So we're averaging over the entire 24-hour period. Okay, so we can deduce that the work that you do every day is right around 2,000 calories. Why? Because you eat roughly 2,000 calories of food every day. So if you were doing more than 2,000 calories of work every day, then your energy reserves would be diminishing over time, and you would eventually starve. Okay, so you know, assuming you have a steady amount of energy stored in your body, you are doing about 2,000 calories of work every day. The amount of food that you eat, the energy contained in that food, is equal to the amount of energy that you're using every day. All right? Work is going to be in joules per second, so we have to convert this calories to joules. And 1 calorie is 4,186 joules. So that means that every day you are doing approximately 8,372,000 joules of work every day. Okay? Now you do that amount of work, okay, over a 24-hour period. So the time is 86,400 seconds. That's the number of seconds in a day. So we have 8,372,000 372,000 joules in 86,400 seconds. And that's right around 97 watts. Okay, 97 watts. If you look at an incandescent light bulb, I guess most people are going to LED light bulbs, which is a good thing. But if you look at the top of an incandescent light bulb, it has the wattage of the light bulb on the top of it. And if you look at the top, oftentimes the power output might be 60 watts or 80 watts or 100 watts or something like that. And so humans are consuming energy at the same rate as a light bulb, essentially. Okay, so I think that's kind of interesting. You're basically as powerful as a light bulb. If we were in person, I have an experiment that we would do to measure your power output, and it's a pretty fun experiment. But there's always someone, so that the power output of a human is roughly 100 watts. There's always someone who does a miscalculation and thinks that their power output is like thousands of watts, which is just not possible. And it's just kind of funny to me because they just accept that. They just believe that they're inherently so powerful. Nope, everyone's power output is about 100 watts. Let's just do one more example. For the last example, let's suppose a car of mass 2,000 kilograms accelerates from, let's say, 0 meters per second to 50 meters per second in 7 seconds. What is the power output of the engine? Okay. So to figure out the work that the engine does, we are going to use the work equals change in energy formula. Okay. So we know that the work done is going to equal the final energy minus the initial energy. So the car starts at rest. So it starts out with 0 joules of energy. And then the car goes up to 50 meters per second, so it has 50 meters per second worth of kinetic energy. So we have 1/2 times 2,000 times 50 squared. Like that. 0.5 times 2,000 times 50 squared. So that's 2,500,000 joules of work was done during that acceleration. Now, that happened over 7 seconds. So the power is work divided by time. 2.5 times 10 to the 6th divided by 7. So that's a power output of 3.6 times 10 to the 5th watts. Okay. Now, if you're familiar with cars, generally speaking, the power output is not measured in watts. They use a different unit of power, which is called the horsepower. 1 horsepower is equal, I want to double check, I think it's 746 watts, but let me double check. Yeah, 746 watts. So if I wanted to convert this to horsepower, 1 horsepower is 746 watts. So I divide it by 746, and I get 480 horsepower or so, which is pretty reasonable. I can remember my family has a boat, and each engine on the boat is 250 watts. So it has two 250 horsepower engines. So add those together, you get 500. So this is pretty reasonable. In reality, the power output of the engine would have to be greater than this amount, because the power. So what often happens with energy is you're doing work. You're doing positive work. You're adding to the energy of an object. And while you're adding energy to an object, something else is taking energy away from the object. Something is doing negative work while you're doing positive work. Okay? This happens if you're on the freeway. Okay? The engine is doing positive work on the car. Okay? So it's adding energy to the car always. But then air resistance, friction, is doing negative work on the car. Okay? So the net result is that no work is done on the car, and it just moves at a constant velocity. All right? When you accelerate a car on the freeway, you're having the engine do more work than friction is taking away. So the engine is putting more energy into the car than air resistance is taking away. Okay, so you're able to gain kinetic energy over time. All right. So you often have this balancing act between the amount of work that one thing is doing versus the amount of work that something else is taking away. So because we didn't account for air resistance in this problem, in order to increase the speed to 50 meters per second, it would actually have to do more work than this, and as a result, the power output would be greater than 480. I'm not sure what the power output of a sports car is, but it would probably be greater than that. Maybe I'll look it up for the chat. Okay, so that's my lesson for today, and I will see you in the Zoom room.